Hello everyone. Today we are moving forward in our journey through the theory of programming languages by focusing on abstract data types, which is ADT, and encapsulation constructs. Now, this topic is foundational in understanding how high level programming languages manage data organization, access control, and modular design. So we'll begin by exploring what abstract data types are, not just tags, queues, or lists, but the idea of separating a data structure's interface from its implementation. Then we'll dive into how encapsulation enforces boundaries in programming by protecting internal state and behavior from unintended interference. Okay, now let's begin with the concept of abstract data types or ADTs. Um, an ADT is a powerful tool in programming. It's a way of thinking about data where we define what operations are possible on a data structure without worrying about how those operations are implemented. Think of it like this: like when you use a stack, you can push and pop or pick, but you don't necessarily know how it's storing the data underneath, so whether it's an array, a linked list, or something else. So the idea is called data abstraction. It allows us to focus on interface over implementation, which is crucial for building modular and reusable code. So to fully support abstract data types, we need to implement a few critical mechanisms in our programming language or design approach. First, we need a way of defining data structure, the blueprint for how our data is organized. Second, we need encapsulation, that is bundling the data structure together with the functions or procedures that manipulate it. When we encapsulate definitions like these into a single unit, such as a class or module, we can compile or load everything at once, making our code more modular and maintainable. Third, and most importantly, we need information hiding. This means protecting the internal structure of the data from being accessed or modified directly by outside code. Only the methods defined within the same encapsulated unit should have access to the internal state. Okay, now as we implement abstract data types encapsulation, encapsulation and alone isn't enough. We must also consider some important design issues that affect how flexible, safe, and efficient the ADT will be. So first, we need to define a unit that combines both the data structure and the subprograms or operations that act on that data. Now, two common questions arise in ADT design, like should access to the ADT be restricted through pointers, or can ADTs be parameterized? So for the first one, this impacts how memory is managed and how users interact with the data. So languages like C or C++ often allow pointer based access, while others like Python abstract that way. In other words, can we design the ADT to work with different types of data like integers, strings, or even user defined types? So this leads to the idea of generic or template based programming, which we'll explore in more detail later. So, one of the most important principle in software design, especially when working with abstract data types, is information hiding. So the idea is simple but powerful. We want to control access to the um, internal details of a data structure that so that external code can't manipulate it directly. Um, so instead, interaction happens only through a well-defined interface. Now, this is usually implemented in two parts. So, the public part or interface, which defines what operations are available externally. This is often limited to methods and constants that users of the entity are allowed to call. Now, the private part, um, which holds the actual data and implementation details. This part is hidden and secure, so only accessible from inside the entity itself. Now, by separating interface from implementation, we gain flexibility and we can change how the data is stored or processed without affecting the external code that uses it, making our programs more secure, maintainable, and modular. Okay, module 2. So, to understand how abstract data types are implemented in programming languages, let's take a look at Module 2, a language that was among the first to offer explicit support for encapsulation using a construct called the module. So, in Module 2, the module is the basic unit for encapsulation. Multiple modules can be grouped together to form libraries of entities, promoting reuse and modularity. When defining a module in Module 2, it is split into two parts. So, first of all, the definition module. This acts as the interface. It includes a partial or full type definition and the headers of the subprograms that manipulate the data. This part is accessible to other parts of the program. Then implementation module. There is this is where the actual logic and internal details reside. It includes the complete data structure and all the subprograms, and this part is hidden from external code, ensuring proper information hiding. And this separation supports both abstraction and security. Now, which is why the concept of modules became foundational in many modern programming languages. Okay, now when working with entities in Modular 2, the visibility of the type's internal structure depends on where the type declaration is placed. So if the complete type declaration is provided in the definition module, the type is called transparent. That means users can see and interact with the full structure, which may defeat the purpose of information hiding. On the other hand, if the definition module only declares the type without specifying its structure, then the type is considered opaque. So this is how we represent two abstract data types. Now here's the key part. So opaque types must be accessed via pointers. Now because the user doesn't know what's inside the type, they can only hold a reference to it. And this restriction ensures that the implementation details remain completely hidden. So, and the user can only interact with the ADT through its interface. Okay, next we'll explore how abstract data types are implemented in ADA, a language well known for its strong emphasis on structure and reliability. In ADA, we can call it ADA or ADA. So, the construct used for encapsulation is called a package. And just like in Modula 2, a package in ADA is split into two parts. Now, the specification package, first of all, this is the public interface, and second, the body package, which contains the private or hidden implementation. Now, these two parts can be compiled separately, but the specification must always be compiled first because it defines what the external code can see and rely on. So the specification package must include the types declaration. But however, to enforce information hiding, ADA allows us to use the keyword private in the type declaration. So this ensures that while the type name is known, its structure remains hidden. Okay, now ADA actually supports three levels of ADTs. First of all is types without information hiding. These are not true ADTs. Then second, types that are declared private, hiding their implementation. Third, types that are limited, private, even more restrictive, with no built-in assignment or equality operations, which forces all manipulation to go through defined subprograms. Okay, so to bring our discussion of ADTs in ADA into practice, let's examine this example, which shows how a stack abstract data type is implemented using ADA's package system. This slide displays the specification package named StackPack. Now, at the top, you can see the type stack type is declared as limited private, which hides the internal details from the user. The constant max size sets a fixed size for the stack. Then we declare four subprograms. Empty checks if the stack is empty. Push adds an element. Pop removes the type element. Top returns the top element without removing it. All of these act as the interface for interacting with the stack. Now comes the private section where the actual implementation details are hidden. Here we define list type as an array of integers with size max size. Then the full structure of stack type is revealed. It has a list to hold the elements and a top sub to track the top index. So this approach clearly separates interface from implementation, one of the core goals of ADTs. It ensures that users can only use the stack through defined procedures, keeping the internals protected. Okay, now we move on to the implementation of the StackPack package, which defines the actual behavior of the subprograms we declared earlier. Now, this is the package body, and it begins by including ADS standard text IO library using with ada.text underscore IO and use ada.text underscore IO. So we'll use this for the library IO standard text IO library. So let's go through the procedures one by one. For first of all, the empty function checks if the top sub index is 0. If it is, that means the stack is empty, so it returns true. Now the push procedure first check if the stack has reached its maximum size using if stk.topsub greater than equal to max size. Now if it has, we output an error message to prevent overflow. Otherwise, it increments top sub and inserts the new element at that position in the stacks list. Now the pop and top procedures are not fully shown, but they would remove the top element and return the top element respectively. So the key takeaway here is that the implementation details are encapsulated inside this package body, hidden from any external user. Only the operations like push, pop, etc. are exposed through the specification. Okay. Now, in C++, we have two primary tools for defining abstract data types, structure and classes. While both can hold data and define operations, the structure lacks built-in mechanisms for information hiding. Now this means it can be used for basic encapsulation, but true encapsulation is not enforced. So while a struct can group related data, it doesn't protect, making it unsuitable for real entities unless used with great care. In contrast, C++ classes are built for proper entity design. They support public members, which are accessible from outside the class, private members, which are hidden and can only be accessed internally, and protected members useful for inheritance. So for true entities in C++, we should always use classes, not structures. So when we work with C++ objects, it's important to understand the lifetime and storage type of those instances. So C++ supports three kinds of instances. Static instances exist for the entire duration of the program. Static dynamic instances are created and destroyed as they enter and exit scope. Think of local variables declared in a function. Heap dynamic instances created using new exist until explicit deallocation using delete. Now there's also an important hybrid case, a stack dynamic object that contains heap dynamic members. So even if the object itself is destroyed when it goes out of scope, its heap allocated parts might persist unless properly cleaned up. This is a common source of bugs like memory leaks in C++. Now, this slide shows a basic example of how we implement an abstract data type or ADT in C++ using a class. So unlike ADA, where the specification and body can be separated, C++ allows us to encapsulate everything in one location right inside the class definition. So a private section to declare internal data members, the pointer, stack PTR, and integers max and top PTR. A public section for the constructor, destructor, and interface functions like push, pop, top, and empty. Now the constructor dynamically allocates memory using new, and the destructor uses delete to free it, showing how heap dynamic memory is handled inside a class. Now this structure supports information hiding by restricting direct access to internal details. Anything that shouldn't be exposed outside the class must be placed in the private section. Okay, now here we'll discuss how Java, C Sharp, and Ruby implement data abstract data types. So all three languages enforce ADTs through classes, not struct or modules. In Java, everything is defined inside a class. There's no standalone functions. Every function must belong to a class. And since variables are handled via reference types, every data structure in Java is essentially treated as an ADT. However, unlike C++, Java doesn't force strict encapsulation. It's just the responsibility of the program to use access modifiers like private, protected, or public to enforce information hiding. Now, the same general principle applies to C Sharp and Ruby. These languages encourage the use of classes and offer tools for encapsulation, but they rely on the developer to apply those principles correctly. Now, C Sharp is heavily influenced by both C++ and Java, but more so by Java. In C Sharp, all objects are heap dynamic, and it uses access modifiers like private, public, and protected, like just like Java. But C Sharp goes a bit further. It introduces internal and protected internal access modifiers. Now, these are particularly useful in cross platform assemblies where access needs to be controlled across multiple modules. Additionally, C Sharp allows methods to serve as both accessors and mutators, which supports cleaner encapsulation. As for Ruby, it's more dynamic. So all class variables are private by default, while methods are public unless specified otherwise. Like interestingly, Ruby doesn't require explicit variable declarations. You just use them as needed. Okay, next let's explore parameterized abstract data types. This concept allows us to define a generic ADT where the types of elements and sometimes even the size size are not specified upfront, but instead provided later when needed. For example, imagine creating a stack where you don't specify whether it will hold integers, strings, or floating point numbers. You define that stack generically and later decide what type to use. Similarly, you can design it without fixing the stack's size ahead of time. So, this form of generic programming is extremely powerful for usability and abstraction. So, languages like ADA, C++, Java, and C Sharp all support parameterized ADTs. In C++ and Java, you have probably seen this in the form of templates or generics, for instance, like stack, integer, or list string, like that. So here this is an example how parameterized ADTs are implemented in ADA. So we can define a generic package where we don't fix the size or data type ahead of time. Instead, we define max size as a positive type and element type as a private type. This allows the rest of the ADT to remain the same, but we replace direct usage of types like integer with the placeholder element type and remove constant like max size from inside the ADT definition. Once the generic ADT is defined, we can instantiate it with specific values. So, for example, here we have package integer stack. We can have like package integer stack is new generic stack 100 integer. So here we have created a stack that holds 100 integers. So instantiating the generic stack with a max size of 100 and the element type as integer. And this mechanism brings flexibility and reusability to our ADT designs. Now let's see how parameterized ADTs are handled in C++. So this is done using templated classes. If we want to change the size of a stack class, we simply modify the constructor to take the size as a parameter. That size value is then used to define the internal array or storage capacity. On the other hand, if we want to change the data type stored in the stack, we define the class as a template using template class type. Here, type is a placeholder that can be replaced by a specific data type like integer, float, or even a custom class when the template is instantiated at runtime. And this approach gives C++ strong support for generic programming, allowing the same class to be reused across multiple data types and sizes efficiently. So in both ADA and C++, parameterized ADTs are handled at compile time. When a new statement is used in ADA, it tells the compiler to generate a new package for that specific instance. However, there is a key difference between the two languages. In C++, if multiple definitions request the same ADT type, the compiler generates only one set of source code. In contrast, ADA generates separate code each time, even if the ADT type is the same. So ADA doesn't optimize code reuse in the same way as C++. So now shifting to Java and C#, both languages implement parameterized ADTs through generic classes. So this should be familiar from your Java 360 course, or if you have any Java course you did before, but we'll just go through it. I will not go into depth here. But just remember that in Java and C#, generics provide flexibility in type definition while maintaining type safety. Okay, as we conclude, let's talk about encapsulation constructs, an essential mechanism in large-scale software development. The main idea here is to organize code into modular units to make programs easier to manage, especially when making changes instead of recompiling the entire code base. We isolate updates to specific chunks. These are called encapsulations. Now, in some languages, we can use nested subprograms to group logically related routines inside their common caller. This feature is not supported in C-like languages. In C++, we use header files. to declare related functions and prototypes. C++ also introduces the friend keyword for controlled access, something we'll explore later or on like in more advanced courses. And if you already took C++ programming language course, you might already know that. Now ADA supports packages that can be compiled independently. These packages can include both data and subprogram definitions, making them flexible containers for ADTs. So in C Sharp, encapsulation is achieved through assemblies, collection of compiled code that can interact with other .NET software. So finally, most modern languages use namespaces to implement named encapsulation, which prevents naming conflicts and keeps code organized. Now, so overall, we can say encapsulation supports modularity, reusability, and maintainability, which are key goals in software engineering or computer science. So that's all for today's lecture. If you have any question or concerns, feel free to email me anytime. Thank you.